Now we have a speaker from another continent. So we have Amira. Hey, Amira. Good morning. Good morning there.
Good morning. Got my coffee.
Okay. So Amira, do you want to try? Do you want to share your slide?
Sure. Okay. Put full screen. Okay. Do you see the full screen? Okay.
Yeah, it looks very nice. So our next speaker
Cool.
is Amira Abbas from UKZN in South Africa. But I think today she's gonna tell us about her work that was done when she was doing an internship in Zurich, right? And I should
Yes.
also say special thanks to Amira because she advertised our symposium. So I know some of the participants that we have now, they became aware of the symposium and came to join us. Thanks to Amira. Okay, so I'll pass this to Amira. It's all you.
Thanks so much, Daniel, and thank you everyone for thank you to the guys at KAIST for inviting me to give this talk. I'm really happy because KAIST is one of my favorite places in the whole world. I love the university. I love South Korea. I had a really amazing time visiting last year already, and I hope to visit again soon when things are better. But yeah, so from UKZN, and I think so now I'm also actually officially affiliated with IBM, and this is really the work that came out of the last couple of months doing an internship with them. So I'm very fortunate to have worked with some really amazing people. So David, Krista, Stefan from IBM, and Aurelian and Alessio from ETH. And there are not that many of us in the talk, so I mean, please feel free to unmute yourself and ask any questions if you have them. And I believe I have like 20 minutes or so to get through the information. So I've like kind of condensed the main findings of what came out of this paper. So if you want to follow along from home, there's the archive link here. Okay, cool. So just, I don't have to give too much background here because this is a quantum machine learning symposium. So I'm sure everybody is already very familiar with machine learning, but I think it's nice to just introduce the motivation for the project and the idea. And really, I think one can start with a very broad framework for classical or quantum machine learning, right? Where you always have some model or some function, and this model typically takes in some data and depends on some parameters. And of course, the goal of any machine learning task is to find an optimal set of parameters for your model such that your model gives you some robust predictions, right? So it gives you useful information for your machine learning task. And as a machine learning engineer, you really have, I think, two main design choices here in your model, right? So the first is how do you parameterize it? So how do you pick these thetas? And then the second main choice is like really what model family do you even choose? So model families, for example, what I will be speaking about in this talk, in this work, is really largely neural networks as statistical models. So these are basically, I think, the two main choices that one has when constructing this kind of framework. And then, of course, from our perspective, we want to answer this question, right? How can we make this model even more robust or even more advantageous by integrating quantum computing? So how can we find a quantum analog to neural networks, for example, such that they are better in some way? And what does that mean to be better? Maybe they are more powerful, maybe they're more expressive. The types of functions that these quantum models can express perhaps are more are larger, are better. And so then I think one needs to take a step back and even ask this question: how do we measure the power of a model, quantum or classical? And luckily, in classical literature, there are a number of ways to do this, right? So I think the most naive way is to just simply count the number of parameters in your model. So intuitively, like just putting more and more parameters into your model, blindly throwing more parameters in, then you should be able to start to capture more intricate relationships between your data and your variables, right? So this is the intuition here. But this is obviously not a very smart way to do it, because just by putting more and more parameters into your model, you could be introducing redundancy in your model, right? So not all the parameters are being used in a meaningful way. So this is not a very elegant way to do this. But then there's also other suggestions. So I think like probably the most well-known one in neural networks is this idea of the VC dimension. And how the VC dimension works, the technical details are not so important, but what I want to point out to you is that while there are some theoretical advantages, so the VC dimension is a way to measure the model's capacity or expressiveness or power, right? So I use these terms interchangeably. But there are theoretical advantages to the VC dimension, but often in practice, it's really difficult to actually calculate it. And the measure itself can be infinite. So what does it mean to compare two models with infinite power? This is not so meaningful. And also, it usually assumes unrealistic assumptions, like you have access to infinite data and all these other things, which are not true in practice. So there are some practical limitations to the VC dimension. So then the last one that I want to suggest to you is something called the effective dimension. And the effective dimension, I think, is really beautifully intuitive. And what it tries to do in a machine learning setting or context is really try to capture what's useful in your machine learning model. So I like this analogy of clouds in the sky, where clouds are embedded in a three-dimensional space, but the space that they actually occupy, their effective dimension is 1.37. And so using this idea of the effective dimension in a machine learning setting, the effective dimension is really trying to capture what is the true size of your model in a typically high dimensional space. Okay, so if we go back then to this picture that I introduced in the beginning, where you have some model that depends on data and parameters, then there are really two mathematical spaces that I want to point out that are important, that are relevant here. And so the first is quite easy to understand, is the space at which you draw your parameters from for your models. This is the parameter space. And then the second space that is, I think, a little bit less intuitive, but more important, is this idea of model space. So this is probably not a very good drawing, but you can think of model space as the space of all your model functions for a particular parameterization. So for example, a point in model space will actually be a distribution, and this distribution corresponds to your model function with a particular parameterization. And so when you're trying to understand the power or the true size of your model, then this is actually the space that's relevant for us, not the parameter space. And for the longest time, I think the classical machine learning community struggled with understanding the relationship between these two. But now I think it's quite clear how one actually gets from parameter space to model space, how to traverse between these two spaces. And this is very, very nicely captured or incorporated by a quantity called the Fisher information, which I'm sure everybody already knows. So I put the definition here and how we approximate it empirically, but this again is not so important. What I want to point out to you is that the Fisher information actually gives us a notion of distance in model space. And in particular, the square root of the determinant of the Fisher actually gives us the volume of a model in model space. So it gives us a notion of size in model space, which is something that's really quite relevant. So now I can finally say what the effective dimension does, right? So it's basically a measure of power, of expressibility, of something that tries to look into this model space. It tries to quantify how large is your model in this space. And more formally, the equation looks quite messy, but again, I think it's very, very nice, very intuitive, very straightforward to actually understand. So what this means here is like the effective dimension, we call it D, of some model M with a full parameter space, capital theta. It depends on some hyperparameters. So the first is, so this hyperparameter gamma here is something that we fix, so you can ignore. And this parameter N is actually the number of data samples that you have available to you. And so the effective dimension of a model is defined as, if you look at this thing in the top here, we have square root of the determinant, and inside here is the Fisher information. And so in some sense, we've kind of got like the volume of the model in the numerator here, right? And this is integrated over the full parameter space. So we're kind of averaging the volume of all the models in the model space. And this is normalized by this V here. And this V is the volume of the parameter space. So, and one thing I also want to point out about that's cool about the effective dimension is that they introduced the number of data samples in the formula, in the equation. And I put this magnifying glass here because you can understand the number of data samples as like this control parameter that allows you to zoom into model space and look at it more clearly with higher resolution. So the number of data samples that you have available to you allows you to see model space more clearly as you increase the number of data that you have. So this is really quite a nice feature, I think. And also, of course, this is really practical and relevant because very often we have finite data available to us. So this was actually introduced, I should say, in this paper here. And we saw this and we thought, oh, this is really, really cool, right? So we should use it. We should try and check what the effective dimension of quantum models looks like as opposed to classical and see if there's anything interesting. But the first thing that we thought would be problematic was the community, especially the classical machine learning community, will come to us and say, why on earth did you use the effective dimension when it's still relatively new in the machine learning context? Why not something more established, something more robust? And so the first thing that we wanted to do is really motivate more formally why the effective dimension is a good measure of power, is a good measure of expressibility. And how you do that is typically in the context of generalization. So in classical machine learning, generalization is basically trying to make a statement about your model class, on how it will perform on brand new information, how it will perform on new data samples, data that it has never seen before. And how this is typically done, theoretically, is through something called a generalization bound. So what does this mean? Well, you can imagine that you can pick a model, and the model that you pick will have some true error associated with it, right? So that's because you haven't picked the perfect model necessarily. So there will be some true error associated with it. And then you can approximate the true error of your model with the data that you have. So you can approximate it with some empirical error. And the difference between this true error and this empirical error is something called the generalization gap, or the generalization error. And so if you want to make a statement about your capacity measure, your measure of power, then it's really, really nice often to bound this generalization, to see if it can bound this quantity, this generalization error. So this is typically bounded by some measure of capacity. So this is exactly what we are arguing the effective dimension does. It measures the power or the capacity of a model. So the first, I think, exciting result that we were able to show was really that we can bound this quantity using the effective dimension, which comes in here. And the technical details, I mean, if you're interested, you can read the paper, we can talk about it afterwards. But I just want to show you that we were actually able to demonstrate this, which I think is quite nice from a classical point of view, even just on its own. Okay, so hopefully what I've managed to convince you of is that the effective dimension is a robust measure of capacity, of measure of power. We also did a few numerical experiments, which I leave out today, but they're also in the paper, which kind of suggest or support that the effective dimension can actually capture this generalization behavior, which is quite nice. Okay, so now we can use it, right? Now we have motivated for it, and now we can finally go ahead and look at different model classes, and see how do the effective dimensions actually compare. So on the classical side, we chose to look at feed-forward fully connected neural networks. Why? Because they are part of the foundation of deep learning theory, I think. And on the quantum side, we wanted to keep things a little bit more in line with what people use in the community right now. So we looked at these parameterized quantum circuits. When I say quantum neural networks, I really mean like a parameterized quantum model. And we call two models comparable in either side if they share the same input size, the same output size, and the same number of trainable parameters in each model. So on the neural network side, this will be the number of weights and biases. On the quantum side, this will be like the number of parameterized operations in the circuit. And in particular, we picked for the quantum neural network a model that we thought would be quite strong, a model that we thought would be quite expressive and powerful. So we borrowed this kind of architecture here. So we've got some data encoding method. So this feature map is taken from this paper, where they conjecture it to be quite useful, quite strong. And the variational form is, I think, quite a straightforward canonical variational form that consists of some parameterized RY rotations, and then some entangling layers, some CNOT gates between every pair of qubits. And then we also do some post-processing. So we do sigma Z measurements on every qubit, and we post-process based on the parity of the output bit string. So in every experiment, we looked at binary classification, but really this can be extended quite trivially to multi-class classification. Okay, so finally, I can show you now the effective dimension. So what you're looking at here is the effective dimension on the y-axis. It's normalized, so the maximum it can go up to is 1. And on the x-axis is the number of data samples that we have available. And as you can see, the quantum neural network has significantly higher effective dimension. And this is for a fixed input size, output size, and number of trainable parameters. But this trend actually persists. So we increase the input size, we increase the number of trainable parameters, and the quantum neural network just does significantly better. And something I also want to point out is that this classical neural network that we choose to plot here is actually the best one that we can find. So we actually brute force search over different neural network architectures just with this fixed constraint here. So that, what does that mean? We have different activation functions that we search over. We have different number of hidden layers, different number of neurons per layer. As long as these constraints are satisfied, we plot the best one. And so this is really quite impressive that we see this large discrepancy. Okay. So then, of course, the next natural question is why, right? Why does this quantum model seem to be so much more expressive as captured by the effective dimension? And if we go back to the definition of the effective dimension, this is really just a function of the most important quantity here is really this thing here, this Fisher information. So we decided to look a little bit more deeply into the Fisher information of these two models and see if there's anything interesting. And it turns out, to me at least, that there is. So what this plot is for each model, we sampled 100 sets of parameters, and we calculated the Fisher information matrix 100 times. And what we plot here is the average distribution of the eigenvalues. So of these 100 Fisher information matrices for each model, we plot the average of the eigenvalue distribution as a histogram. So the values of the eigenvalues are on the x-axis, and this is the normalized counts on the y-axis. And for the first time, this is what personally got me excited, is we see a little bit of a difference between a classical and a quantum model, and maybe this is useful, right? So the distribution of the eigenvalues here is more evenly spread out, as opposed to on the classical side, where most of the eigenvalues are really, really small, if not equal to zero. So this is a highly degenerate Fisher information matrix that is produced on the classical neural network side. And these subfigures in the plot is just the first bin taken out and plotted again. So this is just to illustrate that, like with the quantum model, not all or most of the eigenvalues are not actually zero. Whereas on the classical side of things, this is not the case, right? The Fisher is highly degenerate. And as we change the number of trainable parameters, we increase the model size. This trend with the quantum neural network Fisher spectrum really persists, right? So it remains quite evenly distributed. And also something that's interesting is that the x-axis doesn't seem to change, right? So the condition number is quite stable with the quantum neural network, whereas in the classical neural network, we start to see these really, really large eigenvalues and massive degeneracy, where all of the eigenvalues are just like concentrated around zero. And it turns out that this is actually very consistent with what we see in classical neural networks, this kind of behavior where we have this type of spectrum. And in particular, what the literature tells us is that the spectra is really undesirable. This massive degeneracy corresponds to a very, very flat loss landscape or model landscape. And this is really difficult to optimize. So this actually slows down optimization. And we know on the classical side of things that this is actually quite bad. So then very quickly we wondered, okay, well, is this property of this nice Fisher spectra unique to the model that we picked? Or is it actually a global quantum property? So maybe like other quantum models will also have this. So in particular, we wanted to compare to a model that we thought would be bad, right? So what does that mean? What is a bad model? Well, we simply swapped the feature map. So we swapped the data encoding strategy to something that's quite easy to simulate classically. So we call this the easy quantum model with this easy data embedding strategy, this easy feature map, as opposed to the quantum neural network that we used, where we have entanglement and other rotations that depend on like products of your feature values. So there's more complicated things going on here. But in the easy quantum model, we basically remove this entanglement, we remove these other rotations, and we just have this straightforward feature map. So we would expect this easy quantum model to be less expressive, to be less powerful than our quantum neural network, right? And so then when we go back to look at the effective dimension, this is exactly aligned to our intuition, where we see this drop off in capacity in the easy quantum model. So the effective dimension is lower, the model is less expressive, less powerful, but still interestingly, significantly higher than the classical neural network. Okay, so then the last piece of the puzzle, the last step that we wanted to actually make a comment on is like, how trainable are these models? Because we know classically that that this Fisher spectra is bad for optimization. What does it actually mean on the quantum side of things? If we have a certain Fisher information spectra, then this quantum neural network, will it train better? Will it have better optimization qualities? And so it turns out there are really nice relationships that exist from classical literature that we can already exploit, right? In particular, this relationship between the Fisher information and something called the Hessian matrix. So the Hessian matrix is just the second derivative of your loss or your cost function with respect to your parameters. But intuitively, all this is it's giving you information of the curvature of your loss landscape. And under certain assumptions, certain general assumptions, we can actually the Fisher and the Hessian actually coincide with each other. So this is really nice because that means we can borrow all this nice literature that exists around the Hessian and loss landscapes of models to understand the loss landscape of our models, hopefully. So these are like some classical results that exist. There are very nice papers about the Hessian and the loss landscape. And on the quantum side of things, there are also some work around the Hessian and what this means for optimization. So I put this paper here where they comment on the idea of barren plateaus. So if your model's gradient starts to vanish, then this is really bad, right? This is the phenomenon of barren plateaus because you can't use gradient-based techniques to train your model. And so what they find was that if your model is in a barren plateau, then the entries of your Hessian will also vanish. So that the values of your Hessian will go to zero. So the spectrum of the Hessian will be very, very concentrated around zero. So we quite trivially also extended this idea to the Fisher information. And what we find was that the entries of the Fisher information will also go to zero if your model is in a barren plateau. So this means that the spectra will be, the eigenvalues will be very, very concentrated around zero if your model is in a barren plateau. So now if we go back to these, the Fisher information spectrum of the models, so this is the classical one, which we know is bad from classical literature. And now we look at the easy quantum model, and we can see as we start to increase its size, it starts to become more and more degenerate, right? So there starts to be more eigenvalues around zero. And now we have just shown that this is perhaps bad because if the entries of your Fisher start to go to zero, the eigenvalues start to go to zero, then this is increasing the likelihood of your model being in a barren plateau. So if we had to train these models, then we would expect this quantum neural network to have the best optimization properties, to train the best, to train the fastest. And so this is exactly what we tried to demonstrate in this small experiment. The last thing that I will show you is these training results here, where in the green line, you've got the quantum neural network, which trains to the lowest loss, the fastest, so in the fewest number of iterations for a fixed number of iterations. And the red model is the classical one, which has the largest spread, interestingly, and the easy quantum model is kind of like somewhere in between. And then we also implemented this experiment on real hardware. So it's a toy example, right? So we use a subset of the iris data set. But what was nice was that we could actually train this model on real hardware, and we used the IBM Q Montreal device. Okay, so let me see what I'm doing for time. Okay, so I'm almost done. So what I've showed you is that these well-conditioned quantum neural networks, what does well-conditioned means? It means this one with this particular feature map, this strong feature map, has a very high effective dimension, a high expressibility. It has a more even Fisher information spectrum, which is desirable for a number of optimization reasons, and we can also demonstrate that this model trains better. And this leaves a ton of open questions, right? So while this was a very nice project, there are many, many doors now to open and to follow. And in particular, two things I want to just leave you with is just the next thing that I hopefully plan to address is really deeply investigate, more theoretically, more fundamentally, why this class of quantum models, these quantum neural networks that I showed you, why are they so special? Why do they have high effective dimension and better optimization qualities? And yes. Okay, sorry, I thought I heard someone speaking. And lastly, can quantum models generalize better is the question that I also really, really hope to answer one day, or I hope somebody answers it one day, is can quantum models actually perform better on new data than classical models? And if we can show this, then we have a very very strong motivation for why we should look at quantum machine learning, at least theoretical quantum machine learning, more seriously. Okay, then I'm done.
Thanks, Amira, for a very interesting talk. So, do we have any questions from audience?
Yes, can I ask a question to Amira?
Yes,
Amira, it's a very nice and interesting work. I want to ask you again, from your experience, what is the most trainable, parametric circuit? I mean, there are many models, but if you came across with one of the best, a circuit that behaves in training, I will appreciate if you can share such a circuit model.
Yeah, sure. So what was interesting was like, so we fixed the variational form. So the variational circuit that we look at, we fix it. But what I thought was interesting was that the training, how you can train this model, it depends on how you encode your data. So we used different feature maps that are built into Qiskit. So there's one called the Z feature map and then the ZZ feature map. And for some reason, the ZZ feature map was just giving us all these, it's this model that I call the quantum neural network here. And so it suggests that the feature map actually influences the trainability of your circuit. So this, I think, is something we don't know yet, but we want to really understand more deeply. So this was quite interesting.
Mm-hmm. Okay. Yeah. Okay. Thank you.
Thanks.
I see a question on the chatting board. So maybe I can just read it out, or
Sure.
I mean, you can also read it, Mira, from your screen.
I think
okay,
I can't see the screen. Yeah.
So if you because you're sharing your screen, right? So if you like move your mouse to the top of the screen,
Oh, okay, cool.
I think
Yes, I
there
see
should be
it.
like a
Okay.
tab that just drops out, right?
Yes, got it. Yes, okay, so I see it. When we talk about power of neural networks, are we also talking about the effectiveness given their typical low interpretability? So I'm not sure. I don't know what you mean by their effectiveness and their low interpretability, right? So in short, I'm not so sure what you mean by this. So you're welcome to add some explanation for me, or we can chat, or you can unmute yourself and explain better. But the effective dimension really just tries to capture what parameters in your model are relevant,
so when
right?
I was speaking about effective, are you able to hear me?
Yeah.
Yeah. So when we are talking about effectiveness, I wanted to understand the bit about accuracy and how accurate, because in when we are using neural networks in AI, we have like certain neural networks that are more accurate and effective as compared to some others. So I wanted to understand, when we are talking about power of neural networks, are we speaking and factoring about the accuracy and effectiveness as well?
No. Okay. So thank you. I understand what you mean now. So what I mean by power is really the ability of your model or your model class to express different functions. So what functions can it actually approximate? So how expressive is it from this perspective? So this is not necessarily directly related to the accuracy on data and so on directly. So this is what I mean when I say power, right? And this might not necessarily be always a good thing to have a model that can express infinitely many different functions, because there are also problems with like overfitting and these ideas of that tap back to generalization. And so this is what I mean by power.
Oh, thank you.
Thanks.
Any other questions? Maybe I'll also ask a question. Sorry,
Can I ask a question?
Yeah, go ahead. Go ahead. I'll wait.
Yeah, like as you said, the data you're training on classical and comparing with quantum, but maybe if we are able to get a quantum data, like construct a quantum sensors and their data, so wouldn't a quantum model be better on that? So, then we can increase the model.
So Ria, your audio is a little bit unclear, but I think your question was like, shouldn't we use or shouldn't we can we get a benefit by using quantum data on a quantum model? And I think this is a more general question. So in general, yes, I'm sure there are, and this is also a branch of quantum machine learning where you use quantum data on a quantum computer. But for these purposes of these near-term circuits, so these variational circuits that I showed you, these circuits that depend on parameters, we want to show an advantage with them now, right? We want to show that they're useful with classical data that's really driving classical machine learning forward. And so from this way, these variational circuits are quite robust to noise, and we can actually start to train models using classical data. And maybe these quantum computations or exploiting quantum Hilbert space still give us interesting advantages from even using classical data. So you're totally valid in thinking that maybe quantum models are better suited for quantum data, but this doesn't necessarily mean that they're bad for classical data, right? So I think this is still quite interesting to think about and to study.
Thank you. Thank you very much.
Sure.
Okay, so I'll ask one last question and then we can go to our break. But I found it a little bit surprising that the easy quantum model, if I understood correctly, easy quantum model was where you're only using single qubit gates, right?
Yes. Yeah, this one, this feature.
Yeah, I mean, like, you know, it kind of makes sense that quantum neural network does better than classical neural network. But I was a bit surprised that easy quantum model also does better than classical neural network. Just because, you know, easy quantum model should be really easy to simulate classically. Do you have any?
Yeah.
I mean, you also looked at this Fisher information to see difference there. But do you have any intuition why this also works better?
Yes. So this is a brilliant question. And it really comes down to the effective dimension, right? So the effective dimension, I should say, is also in the limit of n. So if you have infinite data, if the Fisher information has full rank, it will tend to the number of trainable parameters in the model. So it will tend to its maximum. And how quickly it tends to its maximum actually depends on the spectrum of the Fisher. So if the Fisher information is the spectrum is beautifully evenly distributed, then it will tend to the maximum the fastest. So a more even Fisher spectra gives you a better effective dimension. And in the classical neural networks, we start to see this massive degeneracy in the spectra. Let me put it up again. We start to see this behavior here, and this behavior is caused by. So Jan LeCun was actually, I think, the person who discovered this. The reason why this happens is through the nonlinear functions, the activation function. So these nonlinearities that are induced between each hidden layer, they start to cause this shift in the eigenvalues and this concentration around zero. But on the quantum side, we don't have this, right? We don't have these nonlinearities. So this is why the spectra looks favorable. But then we start to see this drop off in this kind of stupid model, because maybe this is a function of barren plateaus, which is something, you know, totally separate. So this is at least how I interpret it. And yeah, my intuition behind why we have this behavior here. This is already well established. And I think this is a little bit more of a question mark, but I think it has something to do with this barren plateau behavior and no nonlinearities. Yeah.
Okay, thank you very much. So let's thank Amira again for very interesting talk. And I think now we can go for a break. So we'll have roughly 10 to 12 minutes break, and we'll be back so in Korean Standard Time, it will be 4:15, whatever that is in your time zone. Basically, we'll be back in like roughly 10 minutes.